All right, let's get started. Hello, everyone. My name is Manivanan Sadasivam. Today, I'm going to talk about upstreaming the Qualcomm modems in Linux kernel, SDX55 case study. I'm working as a kernel engineer at the Qualcomm landing team of Linaro. So I contribute to open source projects such as Linux kernel, U-boot, and Zephyr. And I do maintain several components in these open source projects as well. So this is the agenda for today. Due to the time constraints, I'm going to run through the presentation a little bit faster. So first, I'm going to provide an overview of the Qualcomm Modems Linux kernel, and I'll share some problems we are facing with the downstream code and the benefits of upstreaming with STX55 as the case study. And finally, there will be an upstreaming checklist that includes all the SoC components along with the connectivity. And finally, there will be a complete picture of what we want to achieve. So historically, Qualcomm modems has been categorized into two types based on their processor layout. First one is called the baseband processor modems. The other one is called the multiprocessor modems. The baseband processor modems consist of a microcontroller running an RTOS paired with a modem processor. The modem processor implements the radio-specific protocols such as WCDMA, GSM, LTE, etc. And the microcontroller implements high-level networking stacks such as IPv6, IPv4, and Qualcomm-specific protocols such as DIAC, QMI, etc. And this whole baseband processor modems exposes serial ports to the host machine for configuration as well as for the data connectivity. And the next one is the multiprocessor modems. These multiprocessor modems consist of a ARM Cortex-A grade processor capable of running Linux kernel, and it's paired with the baseband processor running an RTOS. This Cortex-A grade processor implements the communication stacks such as PCIe endpoint, MHI, modem host interface, USB, DIAC, etc. And this whole multiprocessor modems exposes several MHI channels or USB ports to the host machine. And these channels are used for configuration as well as for the data connectivity by the host. Qualcomm modems are further categorized into three types called embedded modems, USB modems, and PCIe modems. The embedded modems are primarily used in the mobile SoCs where the size as well as the BOM cost needs to be reduced. For instance, in the Snapdragon 855 SoC, the X24 modem is connected internally to the system bus. These type of embedded modems are handled by the in-kernel drivers available in the Upstream Linux kernel repository. For example, the remote proc drivers are used for loading the modem firmware as well as controlling the state machine of the modem, such as starting, stopping, and collecting the crash dumps. And there is also RP message and SMP2P for communicating to the modem, and ARMNet driver for creating the network interface in the SoC. Since these embedded modems are not hot pluggable, it requires static device reconfiguration for working. And these device reconfigurations are usually provided by the vendor Qualcomm. Next one is the USB-based modems. These modems interface via the USB ports and exposes several serial ports to the host machine. So these ports are used for communication protocols such as AT, DIAC, QMI, and NET. These USB-based modems are handled by the in-kernel drivers available in the Upstream repository, such as QC serial, option, USB W-WAN, and QMI W-WAN. But unlike the embedded-based modems, these USB-based modems are hot pluggable. That means it can come and go at any point of time and doesn't require the static device reconfiguration. Next one on the list is the PCI-based modems. These modems are primarily used in the PCs as well as in the laptops, and these are interfaced to the motherboard through the PCIe Express slot. And these exposes several MHI channels, such as IPCR and IP hardware software, and QMI, DIAC, MBIM, etc. These MHI channels are consumed by the in-kernel MHI client drivers such as QRouter that consumes the IPCR channel and MHI W1 control driver that consumes the IP hardware and software channels, etc. And finally, there is a MHI net driver that exposes the network interface to the host machine. So as like the USB based modems, these PCI based modems are also hot pluggable. But in a general use case, these are fixed onto the motherboard in the PCIe slot. All of the modems available in the market runs the downstream code, and that comes with the several problems. First of all, not all the source code is available publicly for auditing. Only the Linux kernel source code is available, whereas the RTOS source code running on the baseband processor is proprietary. And for this presentation, we'll only discuss about the Linux kernel code. The apps processor running the software that includes both Linux kernel as well as the user space becomes outdated very quickly. For instance, Linux kernel rolls out a new release roughly every 3 months, and that makes the modem, that makes the modem code, modem Linux kernel, become very outdated. And if you take any modem available in the market, it will be running an older LTS version, such as 3.18, 4.14, and 4.4. And once the device enters the end of life period, it becomes very difficult to update because the backporting of the fixes and features to the downstream code is complex. And often the user space proprietary code is tied to a specific distribution or kernel, and that makes it impossible to upgrade. The downstream source code is not actively reviewed by the open source community because community doesn't care about the downstream code much. And due to this, the downstream code lacks community contributions. So here comes the benefits of upstreaming. So once the modem code base gets upstreamed to the mainline Linux kernel repository, it can be used as it is, and that comes with zero development cost. We only need to integrate the upstream code base into the product so that the app's processor can use the latest bug fixes as well as the features from the mainline Linux kernel repository. With upstreaming, there are several things comes for free of cost. First one is the community code review. Once the modem code base gets upstreamed to the Linux kernel repository, the community will do an active code review and it will use tools and technologies to detect vulnerabilities in the code. It will also contribute back by submitting the bug fixes and sometimes features also. Often, upstreaming is considered as a one-time investment, so we get lifetime maintenance. Once the modem code gets upstreamed to the Linux kernel repository, it will get updated with any API changes happening in the upstream repository. So for this presentation, I'm going to take SDX55 as the case study for upstreaming. SDX55, also known as Snapdragon X55, is a 5G modem chipset from Qualcomm. It, it falls under the multiprocessor modem category as it integrates the ARM Cortex-A7 apps processor and a 5G baseband processor. And it is primarily used as a PCI endpoint device by OEMs, although it is also possible to use USB tethering for data connectivity to the host machine. So I have put together an upstreaming checklist for STX55. So the first category is core SoC infrastructure, and this covers the basic SoC components such as timer, UART, clock, PMIC, GPIO, SMMU, watchdog, etc. And the second category is the storage. It has the SDHCI, which is MMC, NAND, and USB. And the third one is the modem proc. It covers remote proc, mailbox, SMP2P, and IPA. But these three categories are more common across all the Qualcomm SoCs, so I'm not going to cover in detail. There is a final category called connectivity, and that consists of PCIe endpoint and root complex and MHI endpoint stack. And this will be covered briefly in this presentation. So the PCIe endpoint driver in Downstream is represented as a single platform driver not tied to any subsystem. Due to this, there is no clean separation between the PCIe controller and then the PHY. That means all the code related to the PCIe controller and then the PHY part are clubbed onto a single driver. Also, the PCIe endpoint configuration and the iatu configuration are also combined in a single driver. That makes this driver looks clumsy. This downstream PCI endpoint driver incorporates bit 40 hack for IPA. The bit 40 hack implies that the bit 40 of the PCI address gets asserted by the driver before it submits to the PCI IP. Because the PCI IP uses the bit 40 for differentiating between the IPA and non-IPA access. This endpoint downstream driver lacks driver level power management support also. That means there's no runtime suspend or resume. Also, there is no system suspend and resume. And for the PCI endpoint, I have submitted a proposal which completely differs from the downstream implementation. Currently, the driver is submitted to the mailing list and it is under review. The driver is tied to the PCI endpoint subsystem available in the Upstream Linux kernel repository. This driver has a clean separation between the PCI controller and then the PHY part. That means there is a separate driver for the PCI controller as well as for the PHY. And it reuses the iatu helpers available in the PCIe designware core. But for the sake of simplicity, there is no IPA support added in the initial version, but it will come later. Next part is the MHI endpoint stack. The MHI is a protocol which sits on top of the PCIe bus, and it is used by the modems to communicate to the host machine. This MHI bus exposes logical channels through which the configuration as well as the data connectivity happens through the host machine. This MHI endpoint stack is in downstream is represented as a platform driver again, and it is not tied to any subsystem. There is no clean hierarchy between the controller and then the client drivers as like the MHI host stack. The MHI host stack is already available in the Upstream Linux kernel repository, and it is used in several host PCs. This MHI endpoint stack uses a hacky way of invoking the MHI client drivers, and it doesn't use the udo mechanism for signaling the auto registration of client drivers. Also, it doesn't reuse the existing host client drivers. Instead, it uses a separate client driver for the endpoint. And finally, it heavily depends on IPA for two things. One is for transferring the IP packets from the modem, and then the other one is for mapping the host memory. The host memory needs to be mapped in the endpoint device for implementing the MHI functionality. Also, the MHI endpoint stack in downstream depends on device tree for the configuration. It also uses custom notifiers between the PCI endpoint driver and then the MHI endpoint stack to pass various events such as link up and then the busmaster enable. But overall, I found that the code is not very upstream friendly because it uses global variables for catching the context pointer, and overall the code organization is somewhat poor according to the upstream standard. So I'm going to propose a different MHI endpoint stack for the upstream community. It uses the under review PCI endpoint driver, and I have modeled the MHI endpoint stack to be in line with the MHI host stack, which is already available in the upstream repository. This MHI endpoint stack will be represented as a bus in the kernel, where the devices will be created for each logical channel started by the host, and there will be the client drivers binding to these devices. So this is the architecture of the MHI endpoint stack that I'm going to propose. So here, the MHI endpoint stack sits on top of the PCIe bus, and it uses the MHI endpoint controller for carrying out all the PCI endpoint related duties. This MHI endpoint controller is represented as a PCI endpoint function device, PCI endpoint function driver. And and this endpoint function driver makes use of additional notifiers between the PCI endpoint driver and the PCI endpoint function driver for transferring events such as the link up and then the busmaster enable. And these additional notifiers are added in a separate patch set I have submitted to the mailing list. The MHI endpoint stack exposes channels such as IPCR and then the IP hardware 0, and these channels are consumed by the client drivers such as Q router and then the MHI net. But in the future, there will be IPA, which is sitting in between the MHI endpoint stack and then the baseband processor for transferring the IP packets from the modem. And the next one is the iatu. So since I said that we are not going to use IPA in the initial version, we need some way of mapping the host memory in the endpoint device. And that's what iatu is used. iatu is used to map the host memory for ring elements and then the data buffers in the device, in the endpoint device. But the problem with the iatu is it has only 8 windows for mapping the host memory. So we need to do the dynamic mapping for consuming these 8 windows. One more issue with the iatu is that the host address allocated for the ring elements and then the data buffers in the host should be 4K aligned. And that is handled already by the MHI host stack through the bounce buffer configuration. So here comes the code organization of the MHI endpoint stack. The stack will live under drivers bus MHI EP, and the MHI endpoint controller driver will live under drivers PCI endpoint functions. And then the client drivers will live under the same location as like the host client drivers. We'll try to reuse the existing host client drivers at the max possible. So this is the complete picture of what we want to achieve using this modem upstreaming. So we want to demonstrate an end-to-end upstream solution using both Qualcomm Qualcomm host device as well as the Qualcomm endpoint device. So here, SM8250 is used as a host device running the upstream kernel, and SDX55 is used as the endpoint device running the upstream kernel. So the MHI host stack is used along with the PCI root complex driver in the host device. And then in the endpoint, the MHI endpoint stack along with the PCI endpoint driver and IPA driver is used. So the final end goal is to provide the network connectivity to the host over PCIe and also to provide the network connectivity over USB as well. In the later stage, we want to use IPA to accelerate the IP packet handling through the hardware IP channels. And we are planning to use both pass-through as well as the aggregation mode supported by IPA in the future. In MHI, there is also the IP software channels available, and these channels are used to transfer arbitrary data between the endpoint device and then the host. And these data need not be IP packets. These can be anything like camera packets or video data. And finally, we should we are planning to use the modem diagnostic messages or the diag channel. The diag channel exposed by the modem shares the diagnostic messages uh, through the host machine, and we are in the future we might want to consume it for the debugging purposes. So this completes the presentation. Thanks for listening.